Okay, everyone. Morning. So I last saw you on, well, some of you in the tutorials, but in the lecture on Monday afternoon last week. Where we looked at the problem of taking double integrals over non-rectangular regions. Okay, we looked at some examples. This example in the book, and there was an extra example we worked through in that lecture. So just to remind you, some of the basic setting. Well, in this example, so we had a function of two variables x and y. We were given some region in the plane to integrate it over, this region R, and this region R was described as the region bounded by these three boundary curves, y equals 1, x equals 2, and y equals x squared, this kind of curved side. So it's almost a triangle, but not quite. The hypotenuse side is a curve. And the double integral of this function over this region, what it corresponded to, well, if the positive z direction is coming off the screen straight at you, the double integral of this function over this region corresponded to the volume contained in the cylindrical region you get when you continue this region in the plane, when you continue it vertically out of the plane until it hits the surface here. So the surface is some undulating continuous surface above the base plane. But the function is positive, it's on this side, the positive side of the plane. The function is negative, it's behind the screen, behind the ground plane. But what we're calculating is the volume of that region, bounded in 3 dimensions by cylindrical region, bounded at the bottom by this region in the base plane R, and the boundary at the top is provided by the surface, z equals f of xy. Now, because it's non-rectangular, the limits of integration can get complicated. And we described how there's a kind of a dynamic process in filling in these 4 limits here, where you work from the outside in. And if we took it that we were going with the order dx dy, so that dx was the variable for the inner integral, dy was the variable for the outer integral, we had to go from y equals 1 to 4 to capture the region, after we plotted it out and figured out what the boundaries of the region was. So you have to integrate from y equals 1 to 4, and then for a typical y value, represented by this gray line across the region, well, you have to ask yourself, at this y value, what x values do you have to integrate between? Well, we always want to integrate up to x equals 2, but the starting point that we integrate over x is sensitive to the value of y. Namely, for the given value of y, the starting value for the x integral, in order to cover the region, is starting at the square root of y. To integrate from the square root of y up to 2. That's the range of integration for the x integral. And once we have that, when you work it out, you perform the inner integral, and after you make the substitutions, it ends up being just a regular integral of one variable, which you can calculate in a normal way. We also looked at a second example based on a triangle. I'm just going to continue by just showing another couple of examples, another 2 examples. Another 2 examples of changing the order of integration. Okay, so we're not so much worried about actually performing the integration, but rather going through this process of changing the order of integration. So the task here is to change the order of integration. Change the order of integration of this integral here, I, which is the integral from 0 to 2, of the integral from y squared to 2y some function f of xy dx dy. Okay, so we're not caring here what the function is. We're not actually going to integrate it. We just want to go through the process of changing the order of integration. Now, when the region of integration was a rectangle aligned with the coordinate axes, the process of changing the order of integration was trivial. If you want to change the order of integration, you simply picked up the two integral signs, picked up the two differentials, and flipped them. Okay, and this was because it's a rectangle aligned with the coordinate axes. When you want to cover the region with vertical strips, it's the same vertical strip all the time, going from y equals c up to y equals d at whatever the appropriate value of x is between a and b. There's no variation. And similarly, if you want to cover the region with horizontal strips, it's the same horizontal strip each time, from x equals a to x equals b at whatever the appropriate value of y is. Okay? There's no change. That's because it's a rectangle aligned with the coordinate axis. Okay? So you recognize that situation. I mean, well, if you see a rectangle aligned with the coordinate axis, you'll recognize it. But if you see a double integral written down with just 4 constants here, right, 4 constants here, then that's one of these rectangle cases. So you can simply flip the order by flipping the integration signs and their corresponding differentials. However, this is not one of those cases. Okay, these are constants, all right, but these two are not. Okay, these are functions of one of the variables y. Okay, so this immediately tells us that this is not as one of these simple rectangular cases. Okay. So first, we will sketch the region of integration. Sketch the region of integration to appreciate it better. And that will guide us in how to change the order of integration. So we're going to draw a sketch of the xy plane. And you look at these limits of integration. Now remember, these double integrals, they're a pair of nested integrals, one integral inside the other. So the outer integral, so look at the outer integral first. The outer integral goes from y equals 0 to y equals 2. Here we got y equals 0, and y equals 1, say, and y equals 2. So what we're saying is that wherever the region of integration is, it's to be found somewhere within this horizontal band between y equals 0 and y equals 2. So wherever the region of integration is, it's somewhere in here. But then for each given value of y, the x integral begins at y squared and ends at 2y. Okay? So these two values, x equals 2y and x equals y squared, these both describe certain types of curves in the plane, and these are always providing the starting and ending values for the x integral. Now we're used to whatever is conventionally seen curves described as y equals a function of x. So I'll just invert both of them just so I can see them in the traditional way, and then I can put them onto my diagram. So x equals 2y is of course y equals a half x. So that's a straight line. You know, y equals mx plus c. It's a straight line of slope a half and intercept 0. And x equals y squared. Well, that's equivalent to y equals the square root of x. Yeah. So I can plot these curves. So here's x equals 1, x equals 2, x equals 3, x equals 4. So y equals a half of x when when x is value 2, y will be equal to 1. So that's the straight line going through here. Should be intersecting that point there, 4, 2. And then y equals x, or x equals y squared. Well, when x is 1, y is 1. And when x is 4, y is going to be equal to 2. So that's this curve. Kind of comes around here. Okay, so we got this straight line here. That's the line y equals a half of x. And then we got this curve coming right here. That red curve is y equals the square root of x. Are they intentionally crossing at the same point? Well, yeah, because when x is 4, in the line, y is equal to half of 4, which is 2. And in the curve, x is equal to, y is equal to the square root of x. So, yeah, 2 or minus 2. So, yeah, they are both intersecting there. So, what region am I integrating over? Well, y is going from 0 to 2. So then I have to think about a typical value of y somewhere along here in that range. So for that value of y, this inner integral is going from y squared up to 2y. So in other words, it's the x integral is beginning on the curve x equals y squared, and it's going up until it hits the line or the curve y equals 2, x equals 2 times y. So with various values of y, we've got these various horizontal strips. So when you actually draw them, you actually see the region being shaded in front of your eyes. Yeah? So the region of integration is that shaded region. Okay, so now what we want to do is now we can change the order. I want to present I as the double integral over R of this function f of xy, whatever it is. But now I want y as the inner integral and x as the outer integral. So it's again, remember, it's a pair of nested integrals. It's one integral inside the other. So the inner integral is with respect to the y variable. The outer integral is with respect to the x variable. You work from the outside in. So we still want to integrate over the same region. So between what values of the x variable do I have to integrate in order to cover the region? When we look at our diagram, well, I don't want to consider any x's out here because there's no part of the region out here. But I need to begin at x equals 0, and I want to consider all the x values until I get to 4. Okay, so there's parts of the region everywhere between x equals 0 and x equals 4. Once you go beyond x equals 4, there's no more of the region there, and once you go beyond x equals 0, there's none of it there either. So we're integrating from 0 to 4 with respect to x, and then you ask yourself, well, for a typical x value, somewhere between 0 and 4, just put it somewhere. The y integral we will have to want to do is between these two values here. Okay, for this x value, I want to integrate with respect to y, and I want to start at this y value and just integrate up as far as this one. So these values, of course, are the y coordinates of the points on these two curves, okay, located at the value x. So the green straight line is providing the lower limit for y, and the red curve is providing the upper limit for y at that value of x. So these y values are actually functions of x. And they're the functions that we wrote down here when we inverted the original two curves. So I'm always starting to integrate on the straight line, which is y equals a half of x, and I'm always integrating up to until I hit the red curve, which is y equals the square root of x, positive square root of x. Okay, so that is how we change the order of integration. Okay? So if we were given the function f, we could go ahead and integrate it now with respect to the other order. And remember, sometimes integrating in the opposite order can be easier. Due to the structure of the function, sometimes it might be easier to perform the y integral first as opposed to the x integral. So it can be useful to switch between the two orders. Any questions about that directly? Point aspects of that I could clarify. Okay, well let's a bit quicker do another example. So second example, same task. Change the order of this integral, which goes from a half to 1, and then from x cubed to x, f of x y dy dx. So again, the first task here would be to sketch the region of integration. And x goes from a half to 1. So knowing that x begins at a half and ends at 1 means that the region of integration is somewhere in this infinite band, infinite vertical band. Okay, the portion of the plane between x equals a half and x equals 1. But then for a given x value, the y variable varies between x cubed and x. Well, the easiest thing to draw straight away would be the curve y equals x. Just that straight line, 45-degree line. The other curve is, of course, y equals x cubed, which is, well, you know, y equals x cubed kind of looks like this, going through the origin there. So it's this kind of shallow curve to begin with. It goes through the point 1, 1, and let's just choose another point. When you've got x equals a half, the corresponding y value is an 8. So if that's a half, this is a quarter, and this is an 8, so it's going through that. So it's y cubed kind of comes in, some kind of sketch like this. Okay. So we got the straight line, y equals x, and again we got this curve, which I'll draw in red, y equals x cubed, which runs like this. Okay. So for a given x value here, between a half and 1, the y variable integrates starting at x cubed and ending at 1. Of course, for every, I mean, I have drawn them correctly. The red curve is completely underneath the green line, because for any x value less than 1, x cubed will be smaller than x. When you cube something smaller than 1, it gets smaller still. So that's great. So the region of integration is this region here. The region bounded by those two curves between x equals a half and 1. There, this value there. So we can change the order of integration in the same way. So we can write this as an integral over this region R, f of xy, dx dy. But however, now, if we just step back, before we start to write it out, we think about what's going to happen. I want to cover the same region R, so this shaded region here. But this time the outer integral is the y integral. So for a given value of y, see, I have to go from an eighth, y equals an eighth, that's the bottom part of the region. I have to go all the way up to y equals 1. And for a given value of y, I have to integrate across a horizontal strip that will cover the region. But there's two different types of behavior. For low values of y, near an eighth, the horizontal strip, which goes across the region, it always begins at x equals a half. And for the first section, my horizontal strips are always beginning at this straight line here at x equals a half. They're ending at the point on the red curve, which is changing a lot. But then when you go through this middle-ish point, the behavior changes. Then the horizontal strip, the beginning value of x is located on the green line, and the ending value is still on the red curve. So for the starting value of x, there's two types of behavior. For low values of y, x always begins at a half. But once you get past these low values, the horizontal strip is starting on the green line. So that means we're going to need two separate double integrals to handle this. Okay. And the dividing point between the two integrals is this horizontal line here. Okay. So this first integral has to go from y equals an eighth up to y equals 1/2. So from 1/8 up to 1/2. And then the second integral will go from y equals a half all the way up to the end point y equals 1. Okay. So we need these two separate integrals. One to do the double integral over this lower portion, and the second to do the double integral over the top portion. In the lower portion, as we said, the x integral always begins at x equals a half, and it ends at the point on this red curve, which is x equals the cubed root of y. X equals y to the cube. Okay, that's the x equals y to the 1/3 is the equation of that red curve. And for the second half, for a given value of y between a half and 1, that's you're in this top half here, then the x integral is always beginning at the point underneath the green line, which will be the value y. And then again ending at the point on the x coordinate underneath the point on the red curve, which is x equals the cube root of y. So depending on the shape of the region, things can change when you change the order. Okay, here we went from the double integral just being captured by a single repeated integral, single pair of nested integrals, whereas when you change the order, just because of the way the boundary curves work out, you have to bring in two repeated integrals. Okay. Is that okay? Is there any queries you have on that, or any aspects of that you'd like me to clarify? Yeah. Sorry? Well, so the reason is when we write it as an integral like this, a double integral with x as the variable for the inner integral and y as the variable for the outer one, right? When we write it like this, the picture we're thinking of is we're integrating. So if you try to do it in one go, y has to go from an eighth up to 1. In order to capture the shaded region, okay, you have to consider y values from this bottom value here, this is the bottom corner of the region, at y equals an eighth, all the way up to y equals 1. Okay, to the top corner of the region. Okay, so the region is located in this horizontal band between y equals an eighth and y equals 1. Now, if we attempted to do it in a single go like this, what you then have to think about is you think of a general y value in that range between an eighth and 1. So thinking of a general horizontal line. The x integral then has to take that y value and perform an integral across the x variable in such a way that it only goes across the region. Okay. So for different values of y, you have to integrate across different values of x. Now, when you look at these horizontal strips I've drawn across the region, you see every horizontal strip ends on this curve, on this red curve there. But the equation of that red curve is x equals the cubed root of y, or y equals x cubed. It's the same curve. Okay? So these horizontal x strips, they always end at the value y cubed. So that's fine. But when we attempt to fill in this bottom limit, we run into a problem. Okay? Because some of the horizontal strips down here, they are actually all beginning at x equals a half. Because the boundary has this straight vertical side here. So these x strips always begin at x equals a half. So I kind of want to put a half down here. Start at x equals a half. However, once you get past this change point at y equals a half, now the x vertical strips, they begin at a point on this green line. So what point x are they beginning at? Well, if the level is specified by y, the beginning of this horizontal strip here, the beginning of it, the point on the left is y as well. Okay, because that's the point on the line y equals x. It's the 45-degree line y equals x. So for those points, I kind of want to put y as the beginning value. So some of the time, the beginning value is a half, but the rest of the time, the beginning value is y. Well, I can't put these two different expressions down here. So I have to separate them out. So this integral here just takes care of the integral from y equals an eighth up to a half. So that just takes care of this portion here, this lower portion. I'll just move it out here. So this first integral is over that region there. The second integral is over the top half, where the horizontal strips are beginning at the y value and ending at y a third. Okay, so that's the reason it breaks apart into two integrals. Is that okay? Does that help? Good. So it's the tension between these two. Some of the time I need a half there, the rest of the time I need y, so you separate. they need to be treated separately. Okay? Which isn't the case when the integration is done the other way around. When the integration is done the other way around, with y as the inner integral, x as the outer integral, then you're splitting the region up into vertical strips. But the vertical strips are always beginning and ending on the same curve when you look at it the other way. So you don't have that problem. So it remains as a single repeated integral. Okay. Tension between these two. Okay. So that's a few more examples of changing the order of integration. When you look in exercises 1.7, there's a further few examples there. And the ones in example 1.7, at least, I think they're all chosen so that the opposite order simplifies the integral, or makes the integral more doable, so to speak. Okay. So I'm going to flip back to the notes now, and we'll come on to the next section. So the next section has to do with changing the way we're describing our integrals altogether. It's to do with changing coordinates. So first of all, we're going to look back and remember the corresponding thing in the single variable case. And this was more or less known as another name, integration by substitution. So integration by substitution was a technique that was available to you to help you integrate integrals of the form integral of f of x dx, function of a single variable with respect to that variable. You could, if you wanted to, rename or change the variable into a new variable t using some well-understood functional relationship between x and t. So instead of x, you'd replace x with the function x of t, so that you'd replace it with an expression in terms of t. And you also needed to include the derivative dx dt. The new differential dt was kind of equal to dx dt. Or sorry, this was dx of t. The new differential that you want to integrate it with respect to became dx dt. So what we want to describe now is how we do this in higher dimensions, in higher numbers of variables. Well, we make use of, you recall back when we were doing the chain rule section, we introduced something called the Jacobian of the transformation from one coordinate system to another one. And this is where we're going to make some use of it here. This is the rule for how we change the system of coordinates in an integral. So we're supposing here that we're changing from an old system of coordinates x and y to a new coordinate system s and t. And we understand the relationship between the two sets of coordinates. So we know how to express x as a function of s and t and how to express y as a function of s and t. So we can certainly re-express our function in terms of s and t. And we can introduce the new pair of differentials ds dt into the integral as well. Then we also need the introduction of an extra term. Okay? And this extra term is the analogous thing to this derivative dx dt in the one variable case. But in the two variable case, or in the multivariable case, the appropriate thing here is the absolute value of the Jacobian determinant, okay, that we looked at last time. So I better just remind you, remember, the Jacobian determinant The Jacobian determinant was the determinant of the 2 by 2 matrix of partial derivatives. Where the variables on top, the old variables, if you will, the x and y, they index the rows. You got an x row and a y row. And the new variables, the ones on the bottom, the s and t, they index the columns. Or in general, if you're talking about going from a system of n coordinates, x1 up through xn, to a new system of coordinates, s1 through sn, the Jacobian determinant was the determinant of the matrix whose ijth entry was dxi dsj. So this round brackets dxi dsj in general stands for the 2 by 2 matrix of partial derivatives. Okay. Where across the ith row you've got dxi ds1, dxi ds2, dxi ds3. Those are the entries that appear across the ith row. The entries that appear down the jth column are dx1 dsj, dx2 dsj, etc. Okay. It's the ijth indexing of that matrix. Okay, so that's what the Jacobian determinant is. And we take the absolute value of that, and that's the new factor that goes into the integral. So let's look at an example of this. We'll take the example that's in the notes there. So we got this integral, which is the integral over r. The function we're integrating is 1 over x squared plus y squared, dx dy. And the region is the annular region in the plane bounded by the circles of radius a and b in the first quadrant. So the first quadrant in the plane is the top right corner of the plane. We've got two circles, one of radius a, one of radius b. And the annular region is the region between two circles. So this is A and B here. These are circles, not particularly circular. Okay. So this is the region R here. You want to integrate. Now the reason we're bothering to change coordinates is that the Cartesian coordinate system xy is kind of crummy, or it's not well suited to describing this situation. Okay. Firstly, because the region is circular. Okay. And Cartesian coordinates aren't good at describing circles. You need to bring in squares and square roots. And the algebra can be messy, and it can become undoable. And secondly, the function we're asked to integrate, 1 over x squared plus y squared, well, that's quite circular as well, because x squared plus y squared is, of course, the square of the radial distance. The radial distance of a point from the origin with coordinates x, y is the square root of x squared plus y squared. So x squared plus y squared is the square of the radius. So both the integrand, remember the integrand is the function you're integrating, both the integrand and the region here are very circular. Circular. Okay, they're kind of round. So the Cartesian coordinates is bad. Cartesian coordinates is kind of boxy, not appropriate for this. We'd rather switch to the round coordinate system, which is the polar coordinates. So we switch to the appropriate coordinate system. Polar coordinates are theta. Come to the rescue. Now remember, we understand well how to define x in terms of r and theta, and how to define y in terms of r and theta. They're described by those functions there. Remember r theta defines a point by getting its polar angle r and the length of radius out along that radial line until you get to the point. It's how to describe a point with coordinates r and theta. When you consider the triangle formed by that thing there, you get these two relations, x and y are r cos theta and r sin theta. And previously we've worked out, I won't work it out again here, but we worked out previously that the Jacobian determinant was simply the quantity r. Okay, when you form this 2 by 2 matrix here, partial derivatives of these functions with respect to r and theta, took its determinant, we saw that we got this value r. So look back at the chain rule section to see that. I'll be redoing some of these Jacobian calculations in the next lecture for some of the three-dimensional systems. So we'll consider this concept more. Okay, so how does that simplify the integral? Well, here's the integral I. It's again going to be an integral over this region R. Now, when you convert the function 1 over x squared plus y squared to polar coordinates, you get 1 over r squared. Okay? Because x squared plus y squared is equal to the square of the radius. It's equal to r squared. Or if you use these formula, you get this squared plus this squared. So there's r squared in both, and then it's cosine squared plus sine squared. Cosine squared plus sine squared is 1, of course, so it simplifies to r squared. We multiply by the absolute value of the Jacobian. So we multiply by the quantity r. Remember, r is a radial length, so it's always non-negative. We don't need absolute value signs around it. And then dr dt. So a couple of things happen. Firstly, the integrand simplifies to 1 over r. And now we need to think about limits for the integrals. Limits for the two integrals. Now this coordinate system is well suited to that region because the region is circular. So we expect kind of nice limits of integration. So you look at your region and you work from the outside in. So the outer integral is the theta integral. Remember, theta is the polar angle. So you ask yourself, between which values of theta do you need to integrate to capture the region? Well, varying theta means varying this radial line coming out from the origin. So you look at your radial line and you say, well, between which values of radius do you need to consider to cover the region? Well, you need to go from this radius, the flat one, to the vertical one. Okay? So that's integrating from the angle 0 up to pi over 2. Work your angles in radians, of course. So we're going from the angle 0 radians up to pi over 2 radians. So from this angle up to that. That captures the region R. And then you want to think, well, at a general value of theta, in that range, so considering a general radius, between what values of the radius variable r do you have to integrate to capture the region? Well, red pen, we only want to integrate along that bit. So that's the only bit in the region. Of course, these are circles, so we're actually just always integrating from radius A out to radius B. And that's the same for whatever value of theta we choose. The radius we're integrating from A out to B. So actually what we can say is that this region here, in terms of polar coordinates, that region is a rectangle. Because the 4 limits of integration are just constants. 0, pi over 2, and A and B. A and B are just given radii of those circles. Okay? So in terms of polar coordinates, you can say that that annular region here, this annular region here is a rectangle in that coordinate system. Okay? Not a rectangle as we normally think of it, but it's the analogous thing to a rectangle in the polar coordinates. So the integration looks an awful lot easier. If I wanted to find the limits of integration still with x and y, I'd need complicated expressions with square roots and squares. It wouldn't be nice. It'd be awkward. Whereas this is just four constants. It's a lot easier to do. And the integration simply falls out here. The integral of 1 over r is, of course, the natural logarithm of r. We need to evaluate that at a and b. So we're just integrating 0 to pi over 2 times the natural logarithm of b minus the natural logarithm of a. Or in other words, the natural logarithm of b over a. Remember, a difference of logarithms is the logarithm of the quotient. Yeah. Yeah. So now we want to integrate this with respect to theta, but okay, this looks a bit hairy, but there's no thetas in it. It's just a constant with regard to the theta variable. So you're just integrating a constant d theta. So the constant can come outside if you like. And you just get the value theta from integrating 1, and you're evaluating that at 0 and pi over 2. So you just get pi over 2 times the logarithm of b over a. Okay, so the integration is trivial, really. Straight, nothing complicated in the integration, just standard function, integral of 1 over something is the natural logarithm, then integration of a constant. But if you were to have attempted it in the Cartesian coordinates x and y, it would be off. And you would have to make use of effectively trigonometric substitutions, substituting trigonometric functions in for the x and y. So in effect, you would have had to do the equivalent work of transferring to the polar coordinates. But it's just much more cleaner to do it from the very beginning, and to kind of conceptually translate the integral into a completely new coordinate system by making use of this translation procedure, which involves this extra Jacobian factor. So that r there is the absolute value of the Jacobian of the transformation. Okay, there's a couple of further exercises about transferring to polar coordinates in exercises 1.7. So those could feature in your tutorials this week. And we'll do some higher dimensional examples when I see you next. I'll see you next Monday, 2 lectures. Do some work with the 3-dimensional circular coordinate systems and cylindrical coordinate systems. Okay? Yeah.